Hi, everybody. Welcome back to Dave's Math Channel. This is my continuing feature on the Math Lovers book. I'm up to chapter 4 of volume 1, which is on complex numbers, and I'm on section 4.3, which is how to do different types of complex arithmetic, namely all the arithmetic operations. I'm sure you guys are all familiar with addition, subtraction, multiplication, division, even exponentiation. I'll get to at the end. But today I'm going to talk about complex multiplication. This is my third video, by the way, on complex arithmetic, section 4.3. Last time I talked about complex addition and subtraction, which is very easy, pretty much what you expect. But complex multiplication is a lot more complicated, as we'll see. Anyway, let's begin. So how do we define the product of two complex numbers? Well, the way we do it. Remember, I mentioned yesterday that we can use the regular properties of real numbers, which also hold for complex numbers, namely associative and commutative with respect to both addition and multiplication. Also, distributive property. It's mainly the distributive property that will allow us to define the product of two complex numbers. In particular, we use something I'm sure you guys learned when you were in high school called FOIL, first, outer, inner, last. Anyway, let's just go through it. So how would we define the product Z1, Z2? Say Z1 and Z2 are two arbitrary complex numbers. In other words, Z1 we can write as x1 plus iy1, and z2 is x2 plus iy2, where x1, x2 are the real components of z1 and z2 respectively, and y1 and y2 are the imaginary components. That's how we can write two arbitrary complex numbers, but we want to figure out what their product is, z1, z2. Well, we just, we write it's equal to the product of the binomials x1 plus iy1 times x2 plus iy2. Now we, use FOIL to distribute the terms. We say that's first x1, x2, that's the first product of terms. And then we do outer, which is going to be I times, it's going to be x1 times I y2, or ix1, y2 if you like. And then the inner is going to be I y1 times x2, so that gives you I y1 x2. And finally we get iy1 times iy2. So those are the four terms, not simplified, but written out using FOIL, which is just a consequence of applying the distributive law of addition and multiplication twice. So now all we have to do is simplify each of these monomials. Well, the first one's already simplified, x1, y1. And the next two are almost simplified. Let's just write it. The second one is one y2 instead of x y2 x1, because it's just nicer to put the x's first. So we have ix1 y2, and then the third term we can leave alone, ix2 y1. But then the fourth term, notice we have two copies of I in this product, I y1 times I y2. Well, we can use the commutative property of multiplication, move the two i's next to each other. So then we would just get I squared times y1, y2. But I squared is equal to -1. That's the definition of I. So the last term just turns out to be minus y1, y2. So now each term written out, we get x1, x2 plus iy x1, y2 plus I y1, x2 plus minus y1, y2. Now let's reorder the terms. We could do that using the associative property of addition, or commutative property rather. So we can move the real parts together. We get x1, x2 plus or minus y1, y2. And then the imaginary parts are ix1, y2 plus I11, x2. Of course, we can distribute the I. So then when we're done, the final result is x1, x2 minus y1, y2. That's the real part. Plus I times the quantity x1, y2 minus y1, x2. That's the answer. Um, it's even worth memorizing this form. I used to see it in terms of A, B, C, D. Maybe it's a little easier to memorize in that form. So if you have A plus IB times C plus ID, that's just AC minus BD plus I times AD minus BC. That's another way to write this rule. Not too hard to memorize. Uh, but anyway, I wrote it down as equation 4.3 point, what is it? 4.3.3. So yeah, you can just write that as one of your list of identities, as you like. Remember when you were doing algebra, probably learned all these identities for simplifying, different types of products. Kind of doing the same thing with complex numbers here, same idea. And this is a very important formula because it allows you to multiply arbitrary pairs of complex numbers. There's a nice geometric interpretation of this, by the way. I'm not even sure if I talk about this in the book. I think I do later, but maybe I'll just jump the gun a little bit. If you want to multiply two complex numbers geometrically, the way you do it is, remember I said you can think of complex numbers as vectors in what's called the complex plane or on an Argon diagram. Well, it turns out that if you have these two vectors z1 and z2, we don't have to think about the real and imaginary components for now. It's enough to just think of these as vectors, which are sort of like arrows pointing from the origin. Well, then their product is going to be the unique vector whose angle, or argument if you like, that's called the argument, the counterclockwise angle that the vector makes with the x-axis. That is going to be equal to the sum of the arguments of z1 and z2. So the argument of the product is the sum of the arguments, and then the modulus, or the absolute value, if you like, the length of this vector, it turns out, is equal to the product of the length of the vectors z1 and z2. That's a kind of nice geometric interpretation. You can actually prove that this algebraic formula I just derived is also equivalent to what I just said geometrically. It's a little hard to prove that. I'm not going to do it now. I think I do it by the end of the chapter, but like I said, this is just kind of a preview of what's to come. Complex numbers have a lot of really beautiful properties. I hope I've convinced you of this. And I've also convinced you, I hope, that it's not just a vector space. It's a vector space with respect to addition and subtraction. But with respect to multiplication and division, it's an algebra because you can't, in general, at least the way vectors are usually defined, there's not a well-known definition of the product of two vectors, 2D vectors as a vector, but here we do. And this makes it an algebra more than just a vector space. And I'll just finish by telling you that there's a corollary, a very useful corollary, which is just another mathematical name for a consequence of this rule for multiplying two arbitrary complex numbers. What if we're squaring a complex number? So z squared. Suppose we have an arbitrary complex number z equal to x plus iy, and we want to square it. Well, you could again derive it from scratch using FOIL, but we don't have to do that since we can this is just a special case of the formula we just derived. So, if we apply this formula, remember now we only have one x and one y. So if you apply this formula to this special case, you're going to get the real part's going to be x squared minus y squared, and the imaginary part's going to be 2xy. So the answer, z squared, or if you like, x plus iy quantity squared, is equal to x squared minus y squared, that's the real part, plus 2ixy. That's another very useful formula. Anyway, I think that's enough said about complex multiplication. Thank you for watching. Long live math, and I'll see you guys next time. Bye.